Hello, my name is Sarat Balijepalli. My talk is about maintaining large tables in PostgreSQL. I'll be discussing about various performance challenges associated with maintaining large tables in Postgres database, along with recommendations or solutions to have a consistent performance. The talk basically targets database developers and database administrators. Okay, let's get started and do a deep dive on maintaining large tables in PostgreSQL. So, why large tables matter? Scaling data challenges. As applications grow, data accumulates and large tables become inevitable. So, what really happens? More and more users start using the application. The data growth happens. More and more writes, more and more updates, more and more deletes happen on the database. As a result, table size grows. What started with thousands of records, it sometimes goes up to billions of records. So internally on the Postgres side, more and more pages gets added. The index sizes get larger. So this leads to some hidden performance risks. Large tables might appear stable, but gradually, if they are not maintained, we will see slowness in the queries, increased maintenance overhead, and unpredictable performance. So the key insight here is performance doesn't break suddenly; it degrades silently over time. So in this talk, in the next few slides, I'm going to talk about 7 different aspects where things can go wrong and how or what are the recommendations one can follow to make sure that the performance is maintained all the time as the table size grows. So the first one that we are going to talk about is Autovacuum table and index bloat explosion. So the table size grows, there are more frequent updates and deletes on the database. The Autovacuum cannot keep it up with the workload. The workload becomes more aggressive. More and more users start using the application. The tuples start accumulating once the Autovacuum doesn't keep up with the workload. The table size grows far beyond the active data. The indexes also degrade. They also get bloated with more and more data being added, more and more data being updated and deleted. So the storage expands silently. We won't see any immediate failure, but there would be bloat on the table. So what is the impact of this? So more pages, more discretes, more inefficient lookups, more datables in index entries. This will lead to slowness in the queries, random IO increases, read latency increases, the cache hit ratio drops. So this is one of the things we get into once Autovacuum cannot keep up with the workload. The second thing that we could get into is cache inefficiency. So buffer cache trashing will happen. So working set basically exceeds the memory, and as and when new queries come and hit the database, hot pages gets continuously evicted. Queries repeatedly hit the disk instead of cache. So the system behavior, the way it happens is cache reuse reduces, cache hit ratio drops, system becomes more IO bound. So the impact would be the IO latencies increase, even though there are shared buffers. Since the pages are getting evicted continuously, shared buffers become ineffective. The throughput plateaus. The server might have enough CPU resources, but given the workload becomes more IO bound, the throughput plateaus to a point that whatever we do, it doesn't scale. The workload doesn't scale accordingly. The third thing that we will get into is vacuum freeze storms. So before explaining about vacuum freeze storms, I would like to explain about a Postgres parameter, auto vacuum freeze max age. Basically, it's a max allowed age of transaction IDs before Postgres forces a vacuum to prevent wraparound. So this particular parameter is set to 200 million by default. So whenever a table age is equal to 200 million or greater than 200 million, what Postgres does is it triggers anti-wraparound vacuums. So when can this happen? There are two specific scenarios we can think of. One is in write intensive workloads. Table age grows or increases faster, the vacuums are not able to keep up with the workload. That is one situation where we will see the age of the transactions hitting 200 million pretty often. The second scenario is a table is very much insert only workload. So the vacuums never kick in, because vacuums can only kick in when there is there are dead tables getting created on the server. So when the value hits near the 200 million, again there is a very high chance that anti-wraparound vacuums kickstart in the kickstart by Postgres. So why are anti-wraparound vacuums intensive? Because they use uh, heavy IO. The CPU also spike. Basically, they are more. They consume more server resources. So the background maintenance dominates the workload rather than the actual workload. So these anti-wraparound vacuums do the full table scans, look into each and every page, freezes the table tuples, and also visibility map is rebuilt. So the effect of this is we might see query latencies becoming unpredictable if it is not taken care of. The next one that we could get into when it comes to uh, maintaining of large tables is that val volume explosion. So write heavy workloads, we will see uh, millions of inserts, updates, or bulk deletes happening on the server. So val generation rate increases. So if it increases to a point where it starts impacting this throughput, our replica apply capacity, basically replica is not able to sustain the workload, then we start seeing various IO related or disk related constraints on the server. So we could see checkpoints trigger too often. So checkpoints move from being timed to requested, and there would be considerable IO peaks whenever the checkpoint is trying to flush the dirty buffers. And after these checkpoints, we would see full page writes amplify. So that's another thing that we will see. Again, depending on the nature of the workload, we could see something like LW locks related to val writes, which would show the contention around commit latencies. So basically, the system shifts from random data I/O to sequential val-dominated I/O pattern, uh, which um, could create a lot of performance issues. And the adding to that, if the replica is not able to sustain the workload, then replica falls behind. The lag increases. The slot starts retaining a lot of val in it, which could lead to more disk usage, and disk full issues also could come up because it's not able to consume as fast as possible, leading to storage related disk full issues also. So what is the impact of this? So the impact, write throughput spikes, sustained high val generation rate, commit latency as we discussed, if sync and val flush becomes a bottleneck, storage IO saturation, sequential val or checkpoints write both collide, replication lag grows, standby cannot replay val fast enough, buffer cache basically becomes uh, drops, more writes, less useful caching. Checkpoint pressure amplifies spikes, burst IO during flush cycle. So basically, the checkpoints becomes from time to requested. That becomes more busty, and IO becomes a bottleneck. Next one that we could see in very last tables is lock contention amplification. So this could happen in two different scenarios. One, long running transactions, which are like batch updates or ETL jobs, which could be having long running transactions which are holding some hot rows updates or indexes on same tables for a very long time. And the second scenario is high concurrency, again on same rows, indexes, and tables. So this leads to some poor access patterns. So what could happen is we have a transaction or multiple sessions are trying to use the same row. So the row gets locked. Then there are more sessions that are blocked because they want to access the same row that has been blocked by another session, leading to cascading blocking chain. So this leads to system-wide latency spikes. So end users start seeing end-to-end application latencies to increase. So which is not only related to database, but even the application layer, the sessions starts piling up. So even the fast queries get stuck behind the slower ones, or the sessions that got locked. So this is another performance implication we have. The next one is statistics stallness. So as the data volume increases, data distribution changes. The analyzed samples becomes too unrepresentative. So we could have histograms, MCV drift, cardinality estimates become inaccurate. So the impact of this is planner uses incorrect row estimates, misestimates propagate across the joins. Optimizer basically picks an inefficient plan. So ultimately, this leads to slower queries, spike in performance related issues can crop up because of statistics stallness. The next one we could get into is hot update failure. So what is an hot update failure? So it is nothing but heap only tuple. So in Postgres, the MVCC architecture is such that every update, uh, a, the existing row is deleted and a new row version is added. If the new row version is added into the same page, the index entry that points to the page where the row is to the associated row, it doesn't have to change. But if the row that is known as heap only to heap only tuple or heap only tuple update. But if there is no space for the new row version to be added in the page, then the new row version gets moved to the new page. So Postgres is forced to allocate to a new page location. What this would lead is the index entry has to point to the new page where to the new row version. So we'll see cross page plus index churn. So that would lead to more val page splits. So the impact of this is val generation increases, more index page splits can happen, right amplification spikes we could see, increased IO pressure. Again, cache churn, more pages are being touched per update, so more and more pages are getting evicted or being used. Latency increases under write heavy workloads. So these are some of the impacts that one could see in hard update failure kind of a scenario. So what are the different performance optimizations we could do? So first thing and foremost we should try is that partitioning of table. So having a table with one single table with say 500 GB or 1 terabyte is generally not recommended because of all the maintenance issues and the various performance challenges we have talked about. So best thing we could do is, if it is possible, partition the table. So time based partition or key based partition, we could do it. The advantage of that is the it keeps the working set smaller per query. We can partition according to the needs of the application also. For example, we need only 1 month's worth of data and all the older data of in uh, say last 6 months data or 1 year data. The application doesn't need. So we may have one active partition and all the other data in other partition. That keeps the active set uh, uh, into a smaller size compared to the non-use set. So and then we could think about having archival solutions. Basically, maintenance becomes very easy when we start partitioning depending on the application needs. So it makes a vacuum effective, maintenance easy. The index sizes don't grow to a point that it is bigger than the RAM size of the SKU. The lock scope also is controlled. Yeah, the queries become more effective because once we have a partition table, we could start seeing partition write queries in such a way that the partition pruning is happening, and only the data from that active partition from where it is needed is picked up. So there are a few ways we could monitor it once we partition a table. Say the table size growth of the partition can be looked into. We briefly talked about partition pruning. So it is very important when we change from the main table to a partition table that the application changes the queries in such a way that all the queries use the part only the partitions that they need. So the partition pruning is happening. Otherwise, again, we will see the same issue that the database, the query starts looking into all the partitions to retrieve the data, which may not be ideal. We could also look into number of sequential scans, number of index scans that are happening for partition, and then try to see what best and how to improve the performance by adding indexes. So these are some of the tricks and what we could do with the partitioning tables. The second thing that we could and we should definitely look into is tuning of auto vacuum. So there are four things here that we could do when it comes to auto vacuum. One is vacuum parameters. Second one is tuning at the table level. Third one is having the vacuuming done at manually. Fourth one is changing the auto vacuum max freeze age if that can be doable. So let's talk about the parameters that we could change. So if the database schema is such that you have multiple tables with large tables with large sizes, say 100 GB, 200 GB, 400 GB. What we could do is, depending on the workload, we could think of changing the parameters like auto vacuum scale factor, auto vacuum analyze factor, from default 20% to 10% or 5% to make sure with the end goal being that these tables are picked more often and the vacuums are happening more frequently on these tables. We could also consider increasing the cost limit, auto vacuum cost limit, but it depends on the IO that is being used on the server. If the server has enough bandwidth and IOPS on it, then definitely we could consider increasing the cost limit. Make sure that the vacuums run on the tables faster. The second one that we talked about is tuning per table settings. So in scenarios where you have a skewed uh, database schema, say you have one table with 1 terabyte and 100 tables with 1 GB. So in those kind of a scenarios, it might be a good option to tune only the table that is really big, that's a 1 terabyte table. The tuning again can be done at the table level. The same parameters can be tuned. Auto vacuum vacuum scale factor, auto vacuum analyze scale factor, auto vacuum cost limit, and we could also consider something like using something like threshold parameter also. So what you could do is like we could look into how many datables are getting generated, say every 2 days or 3 days. I understand the threshold, put the threshold as the in the table level setting. That would automatically trigger the auto vacuum on the table with that many after that many amount of datables are created. So that's another second thing that we could do. The third thing that we could do is like having a schedule of a regular vacuum, manual vacuum through a cron job. That essentially cleans the database large table periodically. We could take a maintenance window, say once in a week, once in 15 days, or out of business hours, and run these uh, manual vacuums frequently. In scenarios where the vacuum table bloat is too high, as a one off case, we could consider something like PG repack to compact the table and then tune what all the parameters that we have discussed and make sure that the tables don't get bloat to a point that it starts impacting the queries. And the last one that we spoke of is the auto vacuum vacuum freeze age. So in a very aggressive workload kind of a database, what we could do is probably increase the freeze max age from 200 million default to 300 million or 400 million and tune these auto vacuum parameters to give ourselves a chance so that the aggressive anti-wraparound vacuums don't kick in and start consuming the server resources. So how do we maintain and look and monitor the vacuums? Again, ended to pull count. We should periodically keep looking into these table sizes, index sizes. We should look. And again, the most important thing is on all the large tables, how often the vacuum is happening, how long the vacuum is running. When was the last vacuum that ran, and these kind of things where we could definitely look into and monitor it. So PGStat user tables and PGStat all tables is one place we could definitely go and keep monitoring. on how the vacuums or not a vacuum is behaving on the server. The next two that we could do is preserving of the hot updates and controlling the wall pressure. So preserving of the hot updates, there is a table level setting that we could do, the fill factor. So in a very update heavy tables, we could make the fill factor to something like 80%. So what essentially that would give is 80% of the rows are, we will still have some space for the new rows to be inserted. So the idea here is with the fill factor at 80, the new versions of the rows when they get created, they don't get moved to the another page because there is no space left in the current page, but there would be enough there would be space for the row to be inserted into the same page. So that would preserve the heap only tuple update, and also avoid unnecessary index columns in the updates. So that also reduces the hot updates and creates this more val generation. So how could we monitor? There are couple of columns in pgstat user tables or pgstat uh, pgstat all tables. The first one is n2 hot update and the other one is n2 updated. So we could take a ratio and keep monitoring it over a period of time to make sure that we have enough hot updates happening. So controlling the valve pressure, I think this is something very important, given the nature of the workload and the size of the database. Sometimes where we have workloads where we have an insert update kind of a insert and then immediately an update. That means we are doing millions of inserts and then committing. Committing also very often, and updates are also single updates. We could think of doing something like batching those writes. So that would reduce the commit latency on the database. The second thing is definitely tuning of the checkpoints. We need to understand the val generation rate, tune the max val size. It is always recommended to have checkpoints time rather than having requested. More checkpoints requested leads to IO, a lot of IO pressure and other system complications like disk saturation, disk bandwidth consumption, and disk apps consumption. So we could tune the checkpoints. So how do we monitor it? So checkpoint frequency, like what we have been talking about, a checkpoint duration also we could look into how often the checkpoint is happening. So in the older versions we have pgstat bg writer. In the newer versions we have pg checkpointer table that we can look into. Again, for commit latencies, we could look into some of the wait events like val write, val insert, val sync. How many we are getting, whether we could tune something around batching of the large writes. The last two performance optimizations that we could think of is reducing the log contention and keeping the statistics fresh. So briefly, we touched upon the log contention, how it can create the locking chains. So what we could do is like break these large transactions into smaller batches, add indexes where they are missing, so that it reduces the locking scope. Avoid idle transactions. Have timeouts in place like idle in session transaction timeout. Also, it is advised that in a highly concurrent environment, to see whether PG advisory logs can be used from the application level, so that we don't get into a situation where we are seeing a log chain being formed on the database and that is impacting the performance of the database. So how do we monitor? We could monitor PG stat activity, look for wait event type of log, and then see if there is any session that is locking other sessions and that is blocking the other sessions. And also we could see the connection pool saturation. If we have a connection pool that is being used, so one of the things that could be there is that these logs are preventing the sessions to complete, and there are sessions that are just waiting for one of these sessions. They are waiting on each other. So that's another symptom, basically, that can cause an issue. So that we could monitor. The last one is keep statistics fresh. So we discussed about how as the data increases, the analyze might lose relevance because uh, we have data, such a large volume of data that it it's not able to, basically it's not able to estimate correctly. So what we could do is change the default statistics target, increase it for the skewed columns or the columns where we feel uh, optimizer is not estimated properly. That would give more rows. That would give more rows for optimizer to analyze and give better estimates. And also we could run analyze more frequently on large tables. So we talked about the maintaining a manual vacuum periodically. Maybe we could also add manual vacuum analyze so that these tables are vacuumed and analyzed more frequently. And from the server parameter perspective, we could change the auto vacuum analyze scale factor, so that for large tables, these are picked up more often than 10%, which is the Postgres default. So how do we monitor plan regressions? Same query, different plans we start seeing it. Row estimates goes off, the estimated row and actual estimate, there is a mismatch when we see the explain analyze. Then the workload doesn't change basically, but we start seeing there is sudden latency spikes. So all this can lead to uh, uh, the queries being slower, and that can lead to different issues. So keeping the statistics fresh with those two things might help the queries to remain performant on the database. That's pretty much from my side. Thank you, everyone.